and we were discussing about circle diagram and how to draw the circle diagram for a given machine. For that I told you last time that two tests can be performed. One is called block rotor test, another is called no load test. Before I come to that testing, let us now we will be now able to understand this thing. On the nameplate rating of a 3-phase induction motor, nameplate rating, this is important to note, nameplate rating of a 3-phase induction motor. If a motor is there, every motor on its body, it will be written what is the kilowatt of the machine. Say for example, I write 5 kilowatt for 440 volt, 3 phase. 3 phase is 3 phase, 440 volt, 50 hertz, 5 kilowatt, and what else will be written is say 1425 RPM, 3 phase induction motor, 3 phase induction motor, typical nameplate rating, where you will note that on the nameplate there is number of poles of the machine not mentioned in general. Now, the question is what are these things? This 5 kilowatt corresponds to what? This 5 kilowatt corresponds to net mechanical power, full load, net mechanical power output. That is what will be mentioned, not the input, it should not be taken as input. This 1425 RPM, this is the full load net mechanical power output, this is the full load speed, full load and mechanical speed it will be written, full load speed. Now, it is from this full load speed, looking at this, I can decide about the number of the poles. Okay. Because full load speed I know it will be less than synchronous speed, is not, and very close to synchronous speed. Therefore, the number of poles of the machine I can easily find out to be 4, because if the number of poles are 4, then only synchronous speed is 1500 RPM. These facts are known to me. Okay. Therefore, next highest synchronous speed for 2 pole synchronous speed is 3000 RPM, but that cannot be synchronous speed whose full load speed is 1425 RPM, because machine will be running even under full load condition at a speed close to synchronous speed, but just below that, that is the thing 1500 RPM. So, this I can find out, and 5 kilowatt is the net mechanical power output, and this voltage whatever it is the line to line voltage, always line to line voltage. These are the things which will be mentioned. Another thing, full load power factor may be mentioned in some of the machines. Under this full load condition, what is the power factor, or sometimes if it is not mentioned, you will be provided or you can assume that to be some value. Now, you know a well designed motor power factor, full load power factor should not be less than 0.8 as simple as that. I mean, no point in designing a machine whose full load power factor is 0.4, then you are drawing excessive reactive power from the machine. So, power factor if it is mentioned, find full load. Generally, power factor you can assume, even if it is not mentioned, to be 0.8, it may be 0.84 lagging power factor, and it has to be lagging, after all everything is RL. Therefore, from this data what you can calculate is the full load current √3 VLL IL, that is line current. I am not bothered whether the motor is connected in star or delta. Line current is all that matters to me. √3 VLL IL and power factor 0.8. But this is the input power factor. Estimation, what I am discussing now, estimating the input current, input full load current. That is, if the machine is operating under full load condition, what current it is really drawing. Therefore, you know √3 VLL IL, this is input power factor. I have assumed, even if it is not given, input power factor. This should be equated to what? Should it be equated to 5 kilowatt? No, 5 kilowatt is the net mechanical power output. If you have seen the power flow diagram, this thing P in, there were several stages and then you get P net mechanical power output. There were several things, stator copper loss, rotor copper loss, this, that. Then you get, and this is what is given, what I am telling. Therefore, this P net mechanical power cannot be the input power, it must be higher than that. Okay, just to estimate, mind you, I am trying to estimate the full load current. Okay, this motor is given how much current it will draw under full load. Then I have assumed power factor, because I cannot but assume it, reasonable value. Similarly, to get the input power factor, I have to assume this 5 into 10 to the power 3 divided by efficiency. Efficiency of a rotating machine, induction motor, may be 82%, 84%, 80%, but it cannot be as high as 99% as it happens in case of a transformer, because of so many losses present of similar type of similar rated transformer. But nonetheless, this efficiency then also I should then assume reasonable. Only the assumption is that the motor has been designed by somebody which has at least maintained these figures. Input power factor is at least 0.8, efficiency is say at least take say 80%, assumed 80% efficiency. So, it is from these figures I will be able to calculate IL. Why I am telling it is necessary to estimate the input current? Because you have a machine and this current may not be explicitly written on the nameplate, then it is this way you estimate the current, and I am telling you, you will not be far from the actual full load current. This is the engineer's approach. Therefore, this full load current drawn from the supply can be estimated. Okay. This you just keep in mind. Then I come to the test. Test is, as I told you, it is no load test and block rotor test. Induction motor, what is no load test? First let us come to no load test. In no load test, suppose this is the motor, let us assume it to be star connected and the rotor may be cage or wound rotor, suppose cage. This is the rotor, here is your supply. So, under no load condition, you apply the full rated voltage, that is 440 volt here line to line, V rated you apply line to line, and give supply to this and record the ammeter reading and connect better 2 wattmeters and W1 plus W2 gives you the total input power. So, under no opposing torque, no external opposing torque. So, no load means no mechanical, no external mechanical torque, external mechanical torque. Only thing may be friction is present, that is not in your hand. So, under this condition you run the machine. What will be the value of the slip under this condition? It will be very small, as I have told you earlier, always draw this curve corresponding to rated voltage. Then at no load it may be running, if this is 1500 rpm 4 pole machine, it will be running 1480 rpm or 90 rpm, very close to that. Therefore, this branch impedance, this branch, or let me draw it, this branch impedance so S will be, can be assumed to be very close to 0 and this is R2 by S. So, this branch can be thought of to be open, that is this circuit practically does not draw any current. Therefore, whatever power it draws, W1 plus W2, that power must be the stator copper loss, rotor circuit there is no current because S is open, this side is open, okay. S tending to 0, this will be infinite, no current here. So, the whatever power is drawn can be assumed to be this, the power in this parallel resistance, which corresponds to mechanical loss as well as core loss. Core loss will be there because flux is there, and the core loss, as I told you, on the stator it is much higher. Rotor iron body core loss can be neglected because low frequency thing. Therefore, this will be the total power drawn. What I can calculate, and this ammeter reading will be the, so let W be this. So, W will be then this, if it is line to line voltage, root 3 VLL, no load current I naught, and no load power factor is theta naught. Ammeter will record this I naught. Therefore, I can calculate the no load power factor, no load power factor to be W by root 3 VLL I naught. VLL is the rated value. So, no load power factor, that is cos theta naught, is known. Therefore, theta naught is known, theta naught is known, cos inverse that. So, this is the thing I will get from the no load test, and will be of interest to me so far as circle diagram is concerned. How we will see? The next test is the block rotor test. In block rotor test, what you do, the same circuit diagram, anyway let me draw. S equal to 1, that is lock the rotor by holding, do not hold by hand, make some mechanical arrangement so that the rotor is locked, it is not allowed to move. So, S equal to 1 is ensured, that is what the blocked rotor means. Then what you do, in the same way you connect an ammeter and 2 wattmeter. Now, the question is how much voltage should I apply? Should I apply the rated voltage? No. Why? Because under block rotor condition at S equal to 1, the equivalent circuit, you no longer can neglect this x 2 dashed, this will be R 2 dashed by 1, S equal to 1, and here are these branches are there. If you apply full voltage, this always remember the winding resistance and leakage reactances at 50 hertz, these are very small. So, R 1, R 2 dashed, X 1, X 2 dashed are the series parameters which are very small. Therefore, if you apply full voltage, huge current will be flowing, will be drawn from the circuit as if you are almost short circuiting the supply. That you cannot do, because machine may exceed its rated current by many times. Okay? Maybe 15-20 times higher than the rated current of the machine. Rated current, that is why I am telling, you can calculate it by putting have this estimate of the rated current. এটা একটু ক্যালকুলেট করে কত হয় বলবে। You can calculate this rated current from this, and then what I am telling, whatever is this number amperage, I am just calculating and telling you 5000 by 0.8 by root 3 into 440. Oh no, IL, let us calculate this in number. So, it will be 5000 by root 3 into 440 volt into 0.8. Into 0.8 efficiency. So, how much it is coming?
10 ampere
approximately 10 ampere. So, for this machine, suppose I am testing, I know its full load current is 10 ampere. I am telling, if you do not allow the rotor to move and apply full voltage, the currents order may be 10-12 times higher than this rated current, maybe 100 ampere, 120 ampere, because the impedance offered to the supply is then the least. When the machine is operating at full load condition, mind you, this is S equal to some 0.04, this resistance increases manifold and full load current is 10 ampere. But now, with the rotor not allowed to move and you apply full voltage, then this current will be excessively large. So, what is done is this motor is supplied from an auto transformer. So, the supply here should be like this. This here is your motor stator, connect it here, connect ammeter, connect wattmeter and so on. So, it is a must. Do not apply full rated voltage, although 440 volt is the rated voltage, and this is the rotor S equal to 1. Now, slowly increase this voltage applied to the motor. Motor in any case is not going to start because it is not allowed, and you will find ammeter reading is increasing, wattmeter reading is increasing. So, increase this auto transformer voltage till rated current flows, say 10 ampere for this machine, and then you further stop increasing the voltage. Therefore, it is like doing short circuit test on a transformer. While doing the short circuit test, we apply enough voltage to circulate the rated current. Here also a situation like that prevails. Leakage impedance only limits the current. Therefore, I must apply very less voltage. How much less? Okay, while doing the experiment, I will keep and watch on the ammeter reading. Apply such a voltage which will be much less than the rated voltage, and you will find line current is 10 ampere. Then you stop further increasing the voltage and note down these readings. That is the whole idea. Therefore, once again I note down the wattmeter reading, which will be W1 plus W2, I am calling it WBL. This ammeter reading is IBL, and what else I was noting, ammeter and voltmeter and applied voltage. Mind you, here also I noted applied voltage. So, note in this test, note B rated you have applied, here you have applying rated voltage. Note V rated, I naught and W, these are the three things. Similarly, here also note W total power, note the line current IBL, which is supposed to be the rated current, that much, and the ammeter reading IBL to indicate block rotor condition, and the applied voltage. Oh, IBL I wrote 2 times, BBL, applied line to line voltage, applied line to line voltage. You apply. Okay, you have got your readings you have taken, then you can go straight away to draw the circle diagram. How? Let us see. What I will do is, I will choose a voltage scale. So, what I do? I choose a voltage scale. Voltage of course need not be drawn right now. Choose a current scale, that so much centimeter represents so much ampere. Then from the no load test I know I naught and theta naught. So, I will sketch this I naught here to the scale now, nothing left. This I can, after choosing a length here. So, in the circle diagram, if you look at, I have got this point O, this is theta naught, recall. So, this point is O dash, suppose this is O, I have got it. Then what I have done, from block rotor test I know IBL and theta BL. I can calculate in the same way I have done here. Only thing you should note one important thing, during block rotor test this parallel branch can be neglected. Why? Because this current is so high, this can be neglected, that is one way. Physically also I am applying only a fraction of the voltage, flux level will be less, core loss will be less, that magnetizing current too will be less. Therefore, this branch can be neglected, or even if it is there that constant business, I have recorded, mind you, this current in any case I 1. So, from that I will calculate this current I 1. So, theta BL I will calculate in the same way, cosine theta BL is equal to WBL divided by root 3 VBL, whatever voltage I have applied, VL and IBL. Is not? This will be the thing. So, theta BL is known. Now, what I will do, and current scale already chosen, so much ampere is represented by 1 centimeter. So, IBL is known and theta BL is known. Mind you, here where is that point? That point is here, S equal to 1. This is theta BL. Let me spoil this figure, but to understand what I am doing is, it is S equal to 1 I am now looking for. Therefore, you draw a line and this is suppose IBL, this is IBL and this angle is theta BL. And this is the point S equal to 1, S equal to 1, S point. Is it? No, not really. Because of the fact, remember when you draw the circle diagram, what thing I assume? I assume that the applied voltage is fixed, but here you have got this point from no load test by assuming applied voltage is 440 volt if that machine, and while doing block rotor test you have only applied a small voltage. So, these numbers IBL, theta BL of course will not change and WBL must be appropriately converted to the rated voltage. In a circuit, if I know you have applied 10 volt, it is carrying 2 ampere current. If you apply 20 volt, it will carry double the current. So, with the rated voltage divided by VBL, V rated by VBL, whatever you have applied, you must multiply this current IBL to get this IBL corresponding to rated voltage. That work you have to do corresponding to rated voltage, because I know I have not carried out the block rotor test under rated condition. So, that is necessary. So, theta BL and this corresponding to rated voltage, modify and fix up this point. And once you do this, then rest of the thing is simple. I know it is a point on the circle, I know this is a point in the circle. So, I will join these two and this must be a chord, and I know diameter center lies on this horizontal line. So, I will bisect this chord, something like this I will do, I will bisect this chord, and this point will be your center of the circle, and then circle can be completed like this. See, drawing the circle is pretty simple. Then I will tell you how to draw the torque line and output line in the next class. Thank you.